Hi, my name is Gabriella Hod, and this is my second video presentation for Mechanics of Materials. Okay, so the problem says shaft ABC is made of solid section AB of A36 steel and tubular section BC made of A36 steel rigidly bonded to a core of 2014 T6 aluminum. The applied torque at C has a magnitude of 50 pounds-feet and the applied torque at B has a magnitude of 75 pounds-feet. And the lengths of the radii of each section are shown in the picture that was given. It asks us to find the twist angle of C relative to the fixed end, the maximum shear stress in the aluminum, and the maximum shear stress in the steel. And so first thing I'm going to do is I'm going to go over the torques. And the one at C is going to be going in the clockwise direction. The one at B is given here as 75, so I'm going to write that in. That's going counterclockwise. And then I'm going to add another torque, and that's going to be going in the clockwise direction because we want the torques to be in equilibrium. And so since the torque that's going, we have one torque of 50 pounds-foot going clockwise, and we have one of 75 pounds-feet going counterclockwise. That means the torque that we're going to add in is going to be 25 pounds-feet going clockwise in order to make the system in equilibrium. So from here, we can make a torque diagram, and so I'm going to make my torque diagram with the torque on this side so that it mimics the image that we're given. And have our x-axis right here. And so we're going to take the information from the torques that we have and put them on this diagram. And so I'm going to start with the torque at A. And since this is going in the clockwise direction, which would normally be negative, we're going to write on the torque diagram, you write it as the reaction is opposite, and so it's going to be going positive 25, and that's going to go up until B. Then we have our second torque at B is 75, which is counterclockwise, which would normally be positive. But the reaction is going to be opposite, so we're going to go down 75, which leads us to be at negative 50. And our last torque is going to be at C, and it's 50 going clockwise, and so we're going to draw that going up, and so we end up back on the x-axis. So now that we have our torque diagram, we can start solving for our twist angle. And the equation for that is going to be TL over JG. I also have to address that since there are two different materials, we're going to have two different modulus of rigidity. And so for A36 steel, the modulus of rigidity, which is in the book, is going to be 11,200 KSI. And for 2014 T6 aluminum, the modulus of rigidity is going to be 3,900 KSI. And so we'll later use these two values to plug into this equation right here. So now we're going to solve for let's solve for J in this equation. And so we can solve for j of AB and we need to solve for j of AB and for j of BC. And j is the polar moment of inertia. And so for AB, since this is a solid cylinder, we're going to use the equation of pi over 2 times radius to the 4th. And so pi over 2, and our radius is given here as 1 inch. And I solved this earlier, and this gives us 1.57 inches to the 4th. And now we're going to solve for BC. So pi over 2. But since this section BC is not a solid cylinder and it has a hollow portion in that is a different material, the equation we use to solve for the moment of, or the polar moment of inertia is going to be different. And so we're going to have pi over 2 multiplied by the outside radius to the 4th, subtracted from the inner radius to the 4th. And that gives us pi over 2. Outer radius is 1 inch to the 4th, and then the inner radius is given here as 0.5 inches, so to the 4th. And I calculated this ahead of time and got 1.4726 inches to the 4th. So our next step is, now that we have almost all the components for this problem, we need to solve for the twist, we can utilize the torque diagram that we made and the what we found for J in order to get the twist angle. And so the twist angle is going to equal T. Now we're going to have T at AB first. And so from AB we have our length, and it's given as 3 feet, but we're going to convert the 3 feet into inches so that we can stay consistent with our units. And so 3 times 12, 36 inches. And then we have over what we just solved for J here, so it's going to be 1.57 inches to the 4th, multiplied by our modulus of rigidity for A36 steel. Since A36 steel is in the section of AB, it's going to be 11,200 KSI. Now, in order to get the torque of AB, we look at our diagram here, and we can see from the diagram that for the torque of AB from here to here, it's going to be positive 25 pounds per foot, and we're going to want to make this pounds inch so that we can stay consistent with our numbers here. So I'm going to multiply 25 by 12, and that's going to be positive since it's up here. So we're going to get 300 inches pounds times 36 inches over 1.57 inches to the 4th times 11,200 KSI. And calculating that really quickly. This gives us 0.61419 radians. And this is just for AB. And AB is for our A36 steel. Now we're going to solve for the aluminum, which is in BC here. So TBC times, and then our length for BC is going to be 2 feet, and to make that inches we multiply by 12, so we get 24 inches over what we solved for earlier for J of BC, which is 1.4726 inches to the fourth, multiplied by our modulus of rigidity for aluminum, which is 3,900 KSI. And to find BC, we go back and refer to our torque diagram. We see at BC, our torque is going to be negative 50 pounds-feet. And so we're going to convert that to pounds-inches by multiplying by 12 again. And it's going to be negative because of this by looking at the diagram. And so 50 times 12 is going to be 600, and it's going to be negative 600 since it's here. So negative 600 inches pounds multiplied by 24 inches divided by 1.4726 inches to the fourth times 3,900 KSI. And if we solve for this, we get negative 2.507 radians. And so now we have the twist, and to get it into angles, we're going to want to multiply our radians by 180 over pi. And so the 0.61419 multiplied by 180 divided by pi, that gives us 35.19 degrees. And our negative 2.507 multiplied by 180 divided by pi, that leaves us with negative 143.66 degrees. So in order to get the angle from A to C, we add the twist angle from AB to the twist angle of BC. And we can either do that with the radians or the degrees. So let's go radians first. So 0.61419 radian plus negative 2.507 radians gives us negative 1.89 radians. And if we want to solve it for the degrees, we can do 35.19 degrees plus negative 143.66 degrees. And that is going to leave us with negative 108.47 degrees. So these are the same answer, just same answers for the twist angle, whether it be in degrees or in radians. And so this is the answer, our answer for part A of the problem. And so now that we have our answer for part A, the next part B asks us to find the maximum shear stress in aluminum, and the part C asks us to find the maximum shear stress in the steel. So let's write part B here. So let's start with part B first. So in order to find the maximum shear stress for aluminum, we're going to be solving for the portion of the cylinder BC. And so here, let's write, just so we label it, aluminum. Going to be from BC, and we use the equation that T max is equal to T multiplied by C over J. Now we already figured out, since this is going to be T of BC here, this is T of BC. And since we already solved for we know what T of BC is from our previous problem solving for twist, and we know what J is because this is going to be J BC. We can just plug in the numbers that we previously solved for into this equation in order to find the max shear stress of the aluminum. And so the max shear stress is equal to TBC, which is negative 600 inches pounds, multiplied by C. And C was found earlier because that is our radius, and that is 1 inch, over JBC, which is right here, which is 1.4726 inches to the fourth. And we can calculate this. And the result we get is negative 407.44, and that's going to be in PSI, since one of these inches cancel, or sorry, two of them cancel. And that's going to be our T max for the aluminum. And now we need to solve for our A36 steel shear max, which is going to be, since the cylinder has steel from A to B, that's the section we're using, AB. We know that we use the same equation as we did for the aluminum, which is the max shear stress is equal to torque of AB for this portion, since it's for the steel, multiplied by C over J AB, equals, we have our torque of AB, which we had found earlier from the torque diagram, used it in this equation here, so it's 300 inches pounds, multiplied by C, which is 1 inch, divided by J of AB, which is 1.57 inches to the fourth. And we calculate this, and we get 191.08 PSI, and that's our T max for our steel. Okay, so here is my signature for this problem. And I'm just going to go over it one more time really quickly. And so pretty much what we've solved for in this problem is we've found the twist angle of C relative to the fixed end, the maximum shear stress of aluminum, and the max shear stress in the steel. We started off by looking at our torques that were given, and since they weren't in equilibrium, we added a torque at point A, which is of 25 pounds-feet in the clockwise direction. We then created a torque diagram using the torques that were given, and made it based off of the fact that if the torque was going in the clockwise direction, then the reaction would be opposite, and so therefore it would be going positive on the torque diagram, and if the torque was counterclockwise, which would normally be positive, it would go in the opposite direction and go negative on the torque diagram. We then solved for the polar moment of inertia for AB, which is of the steel, and BC for the aluminum. And since BC was hollow, we had to use a different equation. Solving for it, we got these two results. We then utilized the modulus of rigidity that we find in the textbook and the answers that we solved for J, and plugged them into the twist equation, which is right here. and we also utilized our numbers from the torque diagram here in order to find our twist angle, which we solved for both radians and degrees, and we got that for the twist angle of AB, we got 35 degrees, and for BC, we got negative 143.66 degrees. Adding these angles together, we get that the twist angle of AC is equal to negative 108.47 degrees, or negative 1.89 radians. It's their equivalent. And that was part A. For part B and C, we used the same equation for both to solve for both, which was that the max shear stress is equal to torque multiplied by C over J. Since the section we're given for aluminum is BC, we used the torque for BC in here, and we got that the max torque for aluminum is negative 407.44 psi, and then we solved the same way for the steel, which is in section AB, and we got that the max shear stress, sorry, this isn't torque, max shear stress is 191.08 psi.